Hello, welcome to next session. In this session, we will solve HC student mechanic paper of year 2011 of GATE exam. Okay. Question 1 to question 9 carry 1 mark each. Okay. Question 1 is a long rectangular steel block is placed over a smooth cast iron surface. The coefficient of friction between steel and cast iron is 0.4. Acceleration due to gravity is 10 meter per second square. If a force of 20 Newton is applied to the block parallel to the surface, the frictional resistance in Newton offered by the surface to the block is big. So suppose this is the block and weight of the block is W, R is in normal direction, F dash is force of friction and F is the force applied. Okay. Now the force applied is 20 Newton. Okay. And coefficient of friction between block and block and steel block and cast iron surface is 0.4. Okay. Uh, and weight of the block is 10 kg. Okay. So the if we consider the limiting friction, okay, then Rn is equal to W and F dash will be mu Rn. Okay. So from this Rn is 100 and force of friction is 0.4 into 100, that is 40 Newton. Okay. But the applied force is 20 Newton, so it is a case of static friction. So the force of friction will be 20 Newton. So answer will be C. Okay. Next, the stress induced in an unconstrained rod that is heated uniformly depends option A only on the coefficient of expansion, B only on the temperature change, C neither on the coefficient of expansion nor on the temperature change, D both on the coefficient of expansion, both on the coefficient of expansion and on temperature change. Okay. So as the road is unconstrained, so it is free to expand, so there will be no stress generated. Okay. So the stress in the road will be zero. Okay. So neither so answer will be C, neither it will depend on coefficient of expansion nor it will depend on temperature change. But for constrained road, the stress is alpha delta T, then it is dependent on both, so answer is C. Okay. Next. The Euler buckling load for a long slender column with fixed end conditions is 1000 Newton. If the load conditions are changed to fixed free, the Euler buckling load in Newton would be uh, the conditions are fixed end condition. Okay, so both ends are fixed. Then the formula for Euler load is 4 pi square EI by L square. That is given as, sorry, it is 10,000. Okay, that is given as 10,000. Okay, now when the end is free, the formula is pi square EI by 4 L square. Okay, now from the ratio of these two, fixed and free end, we have PF by PFR is equal to 16. Now PF is given as 1000. Okay, so PFR will be 625. The option is the okay. Next, for the beam shown, if the maximum reflection occurs at a distance x from spot P, then which one of the following is true? So here the force is applied at a distance a slightly towards spot P and not at the midpoint. Okay. When the load is applied at the midpoint, the deflection is maximum at this point. Okay, when it moves towards P or one end. Okay, then the deflection also slightly moves uh, towards that end. Okay, but the but it will be close to the midpoint always. Okay, so answer will be A to L, option C. Okay, so when the load is applied at the when the load is applied at the midpoint, the reflection will be maximum at the midpoint, and when the load shift towards one of the end, then the point of maximum reflection also shift towards that end, but stays near the midpoint. So answer is C. Okay, so answer is C. Okay, that is between A minimum x to. Okay, next, for biaxial state of stress defined by sigma xx is equal to 40 MPa, sigma yy is equal to minus 20 MPa, sigma tau xy 30 MPa. The Mohr circle is centered at in MPa. Okay. The center of the Mohr circle, the distance of the center of the Mohr circle from the origin of the Mohr circle is summation of normal stresses divided by 2. Okay. So answer will be 40 minus 20 by 2. That is 10 MPa. Okay. So uh, answer will be C. It will be 10 ampere on axis and the Mohr circle will center of Mohr circle will always be on the axis. Okay. So answer is C. Okay. So x is 10. Okay. A mass attached to a string is swung in a circular path with a uniform angular velocity about horizontal plane as shown. Seen directly from above, which path would the mass most closely follow if the string breaks suddenly at T? Okay, so this is the T point. Okay, and here the when this rope suddenly breaks, the different paths are given. That path can be S, can be R, can be Q, and Q P. So we have to select the right path. Okay, so A is option A is P. Okay, and option B is Q. Option C is R. Option D is S. Okay, when the that rope is broken suddenly or breaks suddenly. Okay, then the tension is released from the rope thread. Okay, then is then then due to release of this tension, the force will be in this direction. Okay, opposite to tension. Okay, initially T was there, but now T is released, so that will go in this direction. Okay, now when the and due to centrifugal force, the rope will go in this direction. Okay, sorry, the stone will go in this direction. So resultant of these two will be R. Okay, so due to tension it will move in S direction. Due to tension and rotation it will move in R. So answer is C, option C. Okay, next, for the beam shown, which of the following are discontinuous at midsection? This is the beam shown. Okay, option A bending moment only. Option B axial force and bending moment only. Option C bending moment and shear force only. The option B axial force and axial force bending moment and shear force. Okay, so this is the beam. Okay, so this beam can be represented like this also, where F is the force, this axial force on the beam. Okay, along the axis of the beam. Okay, and movement of the due to this F, this is distance h. The F h is the moment. Okay, So now taking moment and at this is the rigid sport, so it will provide for example vertical reaction, and this is the roller sport, so it will provide only vertical reaction. Okay. Now taking moment about V, so RAV into 12 plus F into H is equal to 0. So RAV will be equal to minus FH by 12. FH by 12. Okay. Okay. Now there is no vertical force, so RAV plus RBV will be 0. So RBV will be FH by L, H by 12. Okay. So and balancing the horizontal forces, so RH will be in this direction and F will be just so RH will be F. Okay. Now the moment at midpoint is RAV 12. Put in the value of RAV, FH by 12 is 12 so minus FH by 2. Okay. So the bending moment, uh, so as the axial force is F, so uh, and it is changes at midpoint. So axial force diagram will be like this, and it will be suddenly changing at this point. Okay, and bending moment is also the point function at midpoint. Okay, because at the midpoint is point bending moment is has been applied. Okay, so the bending moment at the midpoint will be minus fh, and when we consider the point bending moment, okay, then it will be fh by 2, so it will suddenly change from minus fh by 2 to plus fh by 2, okay. So the bending moment uh, will also not be continuous, okay, but and a shear force at point RAV is FH by 12, okay, that is RAV, okay, and at B it will be so it will come down. So shear force diagram at the midpoint will be continuous. Okay. So answer is B on the axial force and bending moment. These are not continuous. Okay. Next a cylindrical shaft is subjected to pure torsion as shown at point P. Okay. This is a cylindrical shaft and is subjected to pure torsion at point P. The only stress component expected to be non-zero are tau yz is equal to tau zy, okay, b tau xy is equal to tau yx, tau yz is equal to tau zy, c tau xy is equal to tau yx, b tau xz is equal to tau zx, okay. So this is the shaft and torque P is subject to torque P, okay. Now this is y direction, this is x direction, this is point P, okay. So in cylindrical coordinate, there are three directions. First is radial direction, second is circumferential direction, and third is longitudinal direction. Radial direction will be like this, and circumferential will be like this, and longitudinal will be perpendicular to the cross section. Okay. So due to this torque, the stress will be generated in circumferential direction. Shear stress will be generated in circumferential. It will cause a complementary shear stress in the other plane of armature. Okay. So when we consider point P, due to this torque, the shear stress will be generated in this direction, in that x direction. Okay, and uh, it will be on plane on this plane. Okay, so this will also cause a complementary shear stress in this plane. Okay, so answer will be tau xy, tau yz. Okay. Okay. You can see that this is a radial direction, this is uh, theta direction, and this is longitudinal direction. And stress will be added tau theta r. Okay, okay. This direction is r. This is tau theta. This direction z. So, or in our diagram, theta is uh, your x and r is your y. Okay. So the answer will be x, y. So this will be tau x, y. Okay. Answer will be C. Next, a non-magnetic light rigid frame with two magnets attached to its leg rests on a mild steel plate as shown. A spring compressed by an amount delta from its unstretched length connects the steel plate to the center of the frame as shown. Which of the figure below represents the correct free body diagram? So uh, this is the spring. Okay, the steel plate. This is the mass. um, So this is a magnet of mass m. Okay. Now the the spring is being compressed by these. Okay. So the spring force will be in upward direction. Okay. And this force is provided by weight of the this magnet and the magnetic force. Okay. So answer will be A. So mg will be downward, F magnetic will be downward, and normal action will be upward. So K delta will be the compression. So answer is A. Next, question 10 to question 20 carry 2 marks. A cord of negligible mass is wrapped around the outer surface of a 5 kg disc of radius 0.5 meter as shown. Okay, if the disc is released from rest, the angular velocity of disc in radian per second after 3 seconds. So this is disc and its radius is 0.5 and it is released from this cord. Okay, and omega is angular velocity. Okay, the options are you have to find out the angular velocity after 3 seconds. Okay, so after 3 seconds, options are A30, B40, C60, D120. So the various forces and torque. So when the this disc is released, okay, so it will rotate like this, okay, and inertia torque will like this, in direction in opposite direction, and a weight, the weight of the disc is mg will be acting always in downward direction. Okay, now as the disk is rotating about point A, so taking moment about point A. Okay. So it will be I theta double dot is equal to mgr. Okay. I theta double dot is equal to mgr. Okay. Now I is about this point and about, so it is by using parallel extension, I is I naught plus mr square, or I is equal to mr square by 2 plus mr square. So I is equal to 3 by 2 mr square. Putting value in 1, putting in 1, okay, we will have equal to a market theta dash dot is equal to or 2g by 3r, or this is the angular acceleration. Putting the value of g, then we have 40 by 3. Theta double dot 40 by 3. Okay. Now the initial angular velocity, initially there is no angular velocity, it will start rotating at some point. Okay, that point is at that point omega I is 0. Okay, and we have to find out the uh, velocity after 3 seconds. Now we know the acceleration using omega f minus omega I is equal to alpha t. We have this omega f 40 by 3 into 4, 3 into 40. That option B is the right answer. The force in member PR for the truss is shown. The force in member PR. You have to find out the force in this member to the thrust shown. A 12 kilonewton tensile, B 12 kilonewton compressive, C 15 kilonewton tensile, C 15 kilonewton compressive. Okay, now we draw the thrust taking RP reaction the, at the spot P and this part is Q. Assuming this part is Q and RP reaction at this P. Okay, now taking moment about this point Q. Okay, we have only two forces that is done and other is reaction. Okay, so RP into 4 minus 10 into 6. Okay, this will be clockwise, this will be anti-clockwise. So RP will be 15 kilonewton. So this is the upward force, yeah, or upward reaction. Okay, so the so force in the member will be downward direction will be compressive. Okay, so answer is 15 kilonewton compressive. This is the force in member RP. Okay, downward reaction is upward. So answer is 15 kilonewton compressive. Okay, next for the configuration shown, the angular velocity in radian per second of the rigid rod ST is, this is rod ST. Option A 4 by root 3, option B 3, option C 2 by root, sorry 2 root 3, option D 6. Okay, and velocity of this T is given as 6 meters per second. Okay, so let the fixed link as 1, this slider as 2, okay, and this connecting wire as 3, and this slider as 4, okay. So here the I center I12 will be at infinity and I14 will also be at infinity, okay. Now this is I23 and this is I34, okay. Now I now if you want to find out I13, we have to join line 1, 2 and 2, 3. 1, 2 and sorry, 1, 2 and 2, 3. Okay, and line 1, 4 and 4, 3. 1, 4 and 4, 3. Then we will get I13. Okay. Now I13 is the point about which the link 3 is rotating when link 1 is fixed. Okay. So as link 1 is fixed, okay, so link 3 is rotating about this point, okay, and on this link, this point is also there, and this point is also there, okay, okay. Now we have the velocity of this link that is 6, okay. So if omega 3 is the velocity of this link, okay, then Vt will be omega 31, sorry, omega 3, I31, I34, okay, omega 3, I31, I34 is equal to 6 meter per second. Similarly, omega s, sorry, Vs will be I omega 3, V31, I31, I23, okay. Now finding the ratio, okay, that is I31, I34, okay, I31, I34, I31, I23. So that is this by this. Okay. So in this triangle, this is base. Okay, and this is sorry, this is perpendicular. Okay. So this will be I31, I323 will be base by perpendicular, and it will be NL60. So putting the value of Vt, we can find out Vs, that is 2 root 3. Option C is the option C is the right answer. Okay. Next, question number 13. If the diameter of a thin, hollow, homogeneous elastic tube is doubled while retaining the thickness within elastic limit, the ratio of maximum liable torque to weight would Option A remains the same. Option B nearly double. Option C become nearly fourfold. Option D becomes nearly eightfold. Okay. So uh, as a thin tube is given, so thickness is very very small as compared to diameter. Okay. So using torsion equation T by J, tau by D by 2. Okay. So for thin cylinder or thin tube, the J is area into R square. Okay. Here area is pi dt and R is D by 2 square. Okay. So putting this value, okay, we have we will have this tau that is T by pi dt into D by 2. Okay. Okay. And T will be tau pi by d pi dt into d by 2. Okay, now weight of the tube is area into length into density. Okay, weight density, that area into length is volume of the tube, and this rho g is weight density, or rho is mass density, and d is the acceleration due to gravity. So T by W is the ratio of these two. Okay, so this is tau into d by 2 and L into rho g. Okay, L into rho g. Now, when the diameter is doubled, okay, then we will double this d into 2d. Okay, then it will become tau into d L into rho g. Okay, then the ratio of T1 by W1 will be only 2, because T by W is only dependent upon d only. Okay, so answer will be B. Okay, next. A simple mass spring system has a natural frequency of 5 Hz. The static deflection of the spring due to mass is acceleration due to gravity is 9.81 meter per second square, and mass of the spring is negligible. Okay, this is the spring and this is mass. Okay, and this is spring mass system. Okay, now we have to find out the static deflection. We know that omega n is equal to dual deflection. So, and frequency is given. So we have to convert this omega into is given in hertz. Okay. So we have to convert this omega to fn. So 2 pi fn, 2 pi into 5. Okay. So delta is this 0.009 and okay. Meter over answer is the answer. Okay. Next, an unspecified pure bending moment is used to bend an aluminum rod of radius 2.5 mm elastically into a circular ring of radius 2 meters. If the same bending moment is used to bend elastically a copper rod of radius 2 mm, the radius of the resulting ring in meter is elastic modulus of aluminum is 70 GPa and elastic modulus of copper is 120 GPa. Option A 0.702, option B 1.404, option C 1.755, option D 2.808. Okay. So here if the now pure bending moment is used to bend this aluminum rod, okay, elastically, and ring of 2 meters. Okay. Now the radius of the aluminum rod is 2.5 mm. It is converted into ring. Okay, so the the radius of the circular ring is 2 mm. Okay, so now In the bending equation, m by I, E by R. Okay, so m is not m is okay. Now R is your two. Okay, 2 meter. Okay, here in bending equation R is your 2 meter, and E is for aluminum rod is 70 to 10 power 3. Okay, R this 30. Okay, and I is your 5 by 64. Then diameter of the rod active material is just 2.5 mm. Okay, sorry, 2.5 into 2, 5. Okay, so this is the bending moment required to convert the rod into ring. Okay, okay, with the ring radius as 2 meter and the rod radius as 2.5 or diameter as 5. Okay, okay, this is the movement required. Similarly, for copper, okay, so radius is 2 mm. Similarly, for copper, radius is 2 mm and so diameter is 4. And so M it is given that same bending moment is in both the cases. Okay, so M is, let it be M. Okay. So R is not given. Okay, R we have to find out. So equating these two, we can find out R. So that is 1.404 meter. So the radius of ring of copper will be 1.404 option B. Okay. Next, a cylindrical chamber is filled with an elastic material of modulus E and Poisson ratio mu as shown. The piston of diameter 2r is pushed down on elastic material as by, as force F in electric friction, and assuming that the chamber and the piston are rigid, the piston moves a distance of option A Fh by pi r square E bracket 1 minus 2 mu square 1 minus mu B Fh pi r square by E bracket 1 plus 2 mu square 1 minus mu C Fh pi r square E 1 minus 2 mu square 1 plus mu D Fh divided by pi r square E 1 plus 2 mu square 1 plus mu. Okay. So this is the load F and it is compressing this portion. Okay. With its modulus velocity E and mu is its Poisson ratio. Okay. Now the due to this load the compressive stress applied will be or the unit stress will be F by R square. Okay. Okay. As the thickness of the material or the circumferential space or the diameter of the material is not changing, so circumferential strain and circumferential and radial strain will be zero. Okay. So ER is zero, radial strain is zero, theta is zero. Okay. So if sigma theta and sigma are the circumferential stress and the radial stresses, then epsilon r is sigma r by E minus mu. So sigma, so then the radial strain is sigma r by E minus mu sigma theta by E plus as theta is in comparative, sorry, as theta is also theta we have assumed theta and sigma r we have assumed are in tensile nature. Okay, so sigma r by E we have assumed. Okay, so sigma r by E then it will be minus mu theta by E and your PS is in compressive nature, so it is mu PS by E. Okay, so sigma r minus mu sigma theta. Okay, as resistance is zero, from this we have sigma r minus mu sigma theta equal to minus mu PS. Okay, similarly for the circumferential strain we can have this sigma theta minus mu sigma r. minus VPS because circumferential strain is also 0. Okay. Now solving these two, we get sigma r is equal to sigma theta, that is minus mu 1 plus mu PS. So it means if PS is in compressive nature, then it is in tensile nature. Okay. Okay. If PS is in if PS is compressive, so it will be in a direction according to that. Okay. So this is the your sigma r or sigma theta. Okay. Now putting the value, now the longitudinal stream we can have that it will be compressed due to PS by E. Okay. And it will also be uh, compressive when we put sigma, when we consider sigma r and sigma theta. Now if we put the value of sigma r as minus mu 1 plus mu, okay, 1 minus mu, then we can have sigma L is equal to PS by E plus 2 mu square 1 minus mu PS by E. Okay, so decrease in H. This is the strain in this direction. Okay, so there will be change in H. So decrease in H is equal to PSB by E minus mu 2 mu square by 1 minus mu PS by E. Okay, to H. Okay, or the distance moved by the piston is also decreased in H. Okay, okay. Whatever there will be, whatever there is deformation in the material, that will be the movement of the piston. Okay, so PS by E 1 minus 2 mu square. 1 minus 2. So putting a value of PS, we can have option A in our answer. Okay. Next, common data for question 17 and 18. A ductile material has tensile yield strength of 200 MPa. Okay. The stress at yield in MPa under biaxial compression for this material according to Tresca criterion is option A 200, option B 200, option C 80, option D 50. Okay. Within question, the stress at yield in MPa under pure shear for the same material according to von Mises criterion. Option A 100 by root 3, option B 200 by root 3, option C 100 root 2, option D 100 root 3. Okay. So according to, so in the first case you have to consider stress theory. Okay. And yield strength of the material is 100 MPa. According to stress theory, the shear stress will be shear yield stress will be sigma L by 2, so it will be 100 MPa. Okay. Now it is given that equibiaxial compression is given. Okay. So as the stresses in two directions are equal, and then the stress in third direction is zero. Okay. So the maximum stress will be given by the compressive stress in one direction minus zero divided by two. Okay. That will be maximum stress. Sorry, maximum shear stress will be maximum normal stress minus maximum normal minimum normal stress. Minimum stress is minus sigma. Okay, because compression in two directions and in third direction there is maximum stress zero. There is zero. So the maximum shear stress will be sigma by 2. Okay. So for yielding, now we have to put this sigma by 2 is equal to 100. Okay. So this is a shear yield stress and this is maximum shear stress. Okay. So sigma is equal to 200 MPa. So option A is the next. The stress at yield under sorry. This was according to Prescott theory. Now we have to calculate according to von Mises theory. According to von Mises theory, that tau yield is equal to sigma yield by root 3. Okay. So it is 200 by root 3 plus under pure shear for the same material. So, so sigma will be, so tau yield is 200 by root 3. So test at yield. Sorry. So as in the second case, the pure shear is given. Okay. So it means and it is failing at tau yield is equal to 200 by root 3. So pure maximum pure shear we can apply is with tau yield. Okay. So answer is 200 by root 3. Option B is the correct answer. In the second case, there is no biaxial case, only the shear stress, only the pure shear stress is given. So that's why we need to calculate further. We will calculate the tau yield, and that is the maximum tau we can apply. Uh, so, so it will be 200 by root 3. So it will be 200. Okay, answer is 200. Next, common data question 4, question number 9, question number common data question 4. Question number 19 and 20. Okay. A hub outer radius 35.0 mm and inner radius 30.08 mm is pressed to a shaft outer radius 33.0 mm and inner radius 31.0 mm. Okay. For of the length of 40 mm, 40.00. The hub and the shaft are made of steel. E is equal to 200 GPa, mu is equal to 0.2, and the compression fraction is 0.3. The pressure that arises at the interface due to press hit is given by P is equal to ET divided by PET delta divided by 2 R square, where R is nominal radius at interface delta is and delta is the radial interference. P is equal to mm if the nominal is the nominal thickness. The local stress concentration can be neglected in calculation. The hoop stress developed in the shaft, option A minus 60.6, option B minus 30.3, option C 15.7, option D 60.6. Question 20. The maximum torque that can be transmitted by the interference bit is A 1005.3, B 54, C 601.0, D 502.7. Okay. So here the outer diameter of the hub is 35. Okay. And inner radius, sorry, outer radius is 35 and inner radius is 32.98. And just for the shaft, the inner radius is 33. Okay. So the interference will be 33 minus 32.9. Okay. So interference is delta is 0.02. Okay. Thickness is given as 2 mm. R is 33 common radius of the hub and shaft. Okay. So by putting these values, we can get P is equal to 3.673. Okay. Okay. Now considering outer shaft. Considering shaft. Okay. The outer area of shaft is 33 mm, inner radius is 31 mm. Okay. Now let sigma r and sigma theta be the radial and compressive stress at the shaft. Okay. Now we know that the variation of radius, the variation of the radius stress and variation of the hoop stress is given by minus a plus b plus r square and a plus b by r square. Okay. Now at inner radius sigma r is 0. At inner radius sigma r is 0. At outer radius it is that p. Okay, because outer radius of shaft is r naught. Okay. Now putting this value, okay, so sigma r is p. Okay, because it is the real pressure or the shrinkage pressure. Okay, and there is no shrinkage pressure at inner radius. Okay, so by this b and we can have b and a in terms of p. Okay, so this we have b and putting this we can have a. Okay, so once we have A and B, okay, we can use it for finding hoop stress in sorry at outer radius at inner radius. Okay, the hoop stress is given as A plus B by R square. So value of A is this. Okay, A plus B by R square, which is B, where R is your inner radius. For outer radius is 33, so it will be 31 square. Okay, and for inner radius it is 31, so it will be this. Okay, so at outer radius the hoop stress will be 58.82, and at inner radius it will be minus 62.498. Okay, so the average hoop stress will be in the shaft will be summation of these two divided by 2, so it will be 6 MPa. So answer is your so answer is your D. Sorry, sorry. Answer is your A. Okay. Now question number 20. Now the last torque required that can be transmitted. That the torque required that can be transmitted is the same the torque that is required to use the grip between shaft and hub. Okay. Now the grip will be loosened by the friction only. Okay, sorry, by the applied torque only, as there is friction between uh, hub and shaft as they are connected like this. Okay, so we have to overcome this friction. Okay, so mu into pressure is the normal reaction. Okay, so, sorry, is the normal friction force. Okay, that is pressure is the weight, or you can say weight. Okay. Pressure into area is the weight or the shaft by hub and hub by on the hub by shaft. Okay. So that is the weight and that is the frictional force and that is the frictional torque will be multiplied by radius and this frictional torque. Okay. So that is by putting mu is equal to 0.5 and pressure we have found out, okay, 3.673, or it is a stress. Okay, so area pi into diameter of common radius and L 40, okay, 33. So answer is 502,654 Newton mm or 502.654 Newton meter. Okay, so answer is 50. Option D is the next. Linked answer type question. The statement of linked answer question 21 and 22. A 2 kilogram mass initially at rest is acted upon by a time varying force whose profile is shown. Okay, this is the profile of the force. Okay, and this is force in Newton. Or y-axis and time in second on axis. The velocity in meter per second of the mass is option A t cube, option B 2t cube, option C 6t, option D 12t. Okay. The distance traveled by the mass in 2 seconds. Option A 24, B 12, C 8, D 14. D 4. Okay. Here the relation of force is given as F is equal to 6 t square. Okay. Now F is your ma, mass into acceleration. Okay. Now m is given as 2 kg. So a is 2t square. A is also derivative. Okay, derivative. We can have v is equal to p cube by t cube plus c. Okay. Now if we put p is equal to 0, v is equal to 0. Position there is no velocity. Okay. So c will be 0. So v will be t cube. The general equation of v is t cube. So answer is a. Now if we uh, put v is equal to ds by dt, okay, ds by dt is equal to t cube, okay, so then s is t4 by 4 plus c1, okay, now when t is 0, there is no displacement, so s is 0, so c1 is 0, so equation becomes s is equal to t4 by 4, so t is equal to 2, t is equal to s is equal to 2 raised to power 4 by 4, 4 answer, option D is the right answer, okay, thank you all.